Meta-level science, example 3, and this is video 4 of a series of videos on meta-level science. We'll be talking about relativity and ether. Review of previous videos. Science is the mapping of mind, model, data, reality with methodical and continual improvements. At the meta level, a space of models needs to be created with each model being evaluated. The second law of thermodynamics is only applicable to the study of heat capacity. The concepts of information, structure, and order are evolving far beyond entropy. The transfer of energy is far more significant than conservation and is also perpetual. Many physics laws are computational properties of families of models. To maintain intermodel consistency, subparticle models should include complex computational tools, macromotion, and environmental or interstructure energy flows. In this video, we, number one, compare models of the medium of vacuum, includes relativity, and entrained Aether model called subquantum kinetics. No one model that rules them all. Example comparison, not comprehensive. Experts in the field should be doing comprehensive comparisons, not religiously following one specific model. We're going to describe both models at a high level, and talk about comparison techniques, and the comparisons will include data match, predictions, computational features such as complexity, paradoxes, singularities, and also mind features such as usability. High-level model descriptions. Relativity. The space that the model is defined in is used as the medium of the vacuum. This is basically a model with one reflective level, or meta level. The reflective level and operational level are basically locked together. Also, this is a simple functional equation representation. There's a very large space of different ways of representing things, functions being but one methodology. The properties of the space include fields such as gravitational and electromagnetic. Subquantum kinetics is an entrained ether. An entrained ether means that the matter and ether are interconnected and affect each other. Within relativity, the connection between space and the matter is much more strongly locked together with very little room for variability. There is a large family of entrained ether models. We look at only one of the more developed, subquantum kinetics, which was first published in the 1980s. Within this model, there are a small number of different particles and a limited number of reactions where subparticles combine. For example, particle X and particle Y combine to create particle Z. There are only 3 dimensions and 1 time dimension needed. The space medium is ether, composed of these subparticles. Particles, the larger particles, are created via a vortex of reactions of subparticles. And these have been simulated with computers. And also similar simulations or similar reactions have actually been experimented with in the real world in chemical reactions, for example. Subquantum kinetics high-level details. Relativity, quark strings, as well as numerous other physics models can be replaced or are emergent. It behaves similar to quantum and cymatic behavior, where structure appears to be at different gradations. Gravity, electricity, and strong fields emerge from the diffusion of subparticles. Reactions of subparticles create valleys and hills of concentrations of different subparticles. The diffusion of specific subparticles toward and away from the valleys and hills causes the different field effects. Subquantum kinetics variation. We use a slightly extended subquantum kinetics model. We look at micro-macro behavior, extending the standard celestial atomic subparticle view. We assume the spin of ether within particles modifies the behavior of ether outside of particles, and vice versa. The spin behavior is more cymatic-like, where gradations have small internal variations as opposed to being discrete. The standard subquantum kinetics models electric behavior with the diffusion of two subparticles, xon and yons, which diffuse in opposite directions because of the subparticle reactions, which cause hills for xons when valleys are caused for yons, and vice versa. Here we look at magnetism as being a smaller gradation of diffusion, where the diffusion is insufficient to cause an electric flow, but instead causes a magnetic flow. Note, the standard subquantum kinetics electrogravitics works with the atomic particle view. Comparison techniques. There should always be multiple models, including multiple spaces of models. Comparison is an evaluation of when and how to use each model. Models have, do, and will always fail. How can the evolution of science be expedited? Don't just wait for the followers of an old model to die off, as Kuhn noticed in his research in the 1970s. We need to use meta-level science to do methodical and continual comparison of the space of models. Quantification of comparison can be by count or other methods of advantages of each different model. With today's technology, databases can and should be maintained. While there are thousands of articles criticizing relativity, it is not a count of articles nor of scientists. Note that the following comparison is not methodical, but rather an example of how to do a comparison. Categories of comparison 1. Data. Does it match the model? Is the data representative of reality? What is the breadth of data? All of these are indications of goodness of a specific model. Predictions. Is there a qualitative prediction history? Is it easy to make predictions? Are quantification tools available? Are simulation tools available? Again, these are all examples of goodness of a specific model. Categories of comparison 2. Computational features. What's the complexity, such as the number of elements, equations, dimensions, levels? Are there paradoxes, points where the model collides with itself? Are there points of singularities, where the model breaks down? For example, division by zero. Are there inconsistency, system-wide collisions within the model? Is there inter-model consistency, where the full system contains integrated models, where the same type of model is used throughout? Are there gaps, domains where the model has no applicability? Openness. Is there room for the model to evolve? This is very important within computer science, and it is also very important within a scientific modeling methodology. for you will always run into new data. Can the model evolve without adding kludges? The mind. Is the model understandable and accessible to a large group? Usability. Are there tools making the model easy to work with and quick to work with, efficient to work with? We now move on to the comparison, first looking at data. Matching data. Relativity states that the speed of light and gravity are constant. The Michelson-Morley experiment measured the speed of light with mirrors in a university basement and measured a very slight variation that was so slight it was treated as no variation. This result also fits an entrained Aether model, but not a non-entrained Ether model. Dayton Miller repeated the same experiment at a higher location, Powell Observatory, and observed a distinct variation in the speed of light. This result only matches an entrained Ether model. Science Set Free by Rupert Sheldrake. In this book, Rupert reviewed the speed of light and gravity data from 1928 to 1945. He discovered that both varied beyond the margin of error in a vast array of cases. He brought this to the attention of the metrology community and was told that in 1970 they modified the measuring equipment to auto-adjust the data to a defined speed of light value so that variations would no longer be seen. Garestian in 2002 combined gravity variation data and determined that it was varying with respect to sidereal time or with respect to how the Earth was traveling through space. These results are only valid within an entrained Ether model. Based upon Rupert's writings, it appears that neither the metrology community nor Rupert Sheldrake understood that the speed of light and gravity constants were based on a specific model, relativity. The metrology community thought they needed to adjust the measuring tool. They did not think that to go back to the physicists and talk to them about the model. Rupert just thought that the assumption that there are constants was wrong. He did not appear to know that there was a very specific model behind the constants. The alternative physics community, however, knows full well that Rupert's work disproves relativity, but this is not news to them as they have collected almost 3,800 papers saying the same thing, and you can see the link and follow that for more details about that. Microscience, or too much specialization, has created a significant lack of understanding. What went wrong? When you deny data, models become religious dogma. While any model can be hacked to make it fit the data, the above invalidates relativity. Why is relativity still in the textbooks? How can the community get it so wrong? Community models being wrong are actually not the exception, but are rather the rule. Microscience, spaghetti science, and greed science always occur if refactoring is not methodically and continually done, as discussed in the first video. In many ways, the current academic model prohibits refactoring. Scientists can't change predecessors' models. They can only add refinements. While relativity is basically dead at the very beginning of this comparison, the purpose of the presentation is to show a broad spectrum of elements of meta-level science comparison. So we continue. We will also see numerous advantages of subquantum kinetics along the way. Basic data questions. We take a side trip here to ClimateGate to see additional data issues. Basic data questions include: what is the depth and breadth of the data? Is there a statistical lie? Can billions of years of data be investigated while only a few years are used for a false trend? ClimateGate. The sea level over the last 12,000 years has risen about 400 feet, which is similar to other patterns throughout geological history. The media, however, is harping about 1 to 2 inches of local changes, which is simply noise. There is similar media hysteria with respect to noise in temperature and CO2 data, where greater amounts of CO2 actually mean greater plant growth, which is beneficial to the world. Farcical implications are being made that this data noise will create an unstoppable snowball of future change. And this is very inappropriate. What is the number of diverse data sources used, and are they appropriately balanced? ClimateGate. Hundreds of sources for predictions have been identified. However, claims are being made that the UN is fudging formulas so that only a couple actually appear, a couple of these sources actually appear in the end result. This is another thing that needs to be investigated whenever you are looking at data. You have to look at the data sources, you have to look at the actual instruments. Have the instruments changed? And that also has been a concern in the analysis of the data. You need to have a scientific depth of analysis when looking at the data. There is never any simple analysis for data. It's always an involved and deep search, because whenever you're looking at data, you are dropping tremendous amounts of information. You're always doing a gross approximation, as discussed in video 1. More basic questions. Does the data match the model? And this was covered in the subquantum kinetics relativity discussion above. Is the data representative of reality? ClimateGate. Are airports or rural locations representative of temperature? Are buoys or ships more representative? Ships and airports produce significant amounts of their own heat, fudging data. Unfortunately, with ClimateGate, the ClimateGatists, UN, etc., are using the ships and airports versus the buoys in more rural locations, which are more representative. ClimateGate. How close to reality can a limited set of geographic points be? Can they be precise to tenths of a degree? Again, the number of points used is very, very small and not representative of the entire globe. And far too many assumptions are being made in the interpolation of the data to be precise to degrees, let alone tenths of degrees, which is one of the things that's being claimed. So a maturity of analysis of the data and what the accuracy of the data can be based upon the data points being used and how representative they are is absolutely essential in any data analysis or correlation to reality. ClimateGate. Are all data sources of CO2 being used? Human CO2 production is such a small percentage, it should be considered noise. Volcanoes and other sources vary the CO2 production data so dramatically that, for example, one volcano in Iceland can represent basically a third of all European CO2 production. Other data questions. Meaningless questions. What percentage of scientists favor a specific model? Inconsequential. All you need is one scientist. You don't even need any scientists. All you need is the data and the models. ClimateGate. The media claims there's a 97% agreement with a specific model. However, investigators have actually looked at that data and that analysis and have found, after review, the source of data is actually only 0.3% of scientific papers where there was actually agreement with a specific model that they were pushing. Most scientists don't have an opinion, for the data and the model have to speak for themselves. Models only match data in limited ways. Greed, political, and economic science. Something natural always happens, cannot be avoided. You need to have tools to minimize it. ClimateGate. Large governments, banks, conglomerates, and the scientists they employ will benefit greatly from the only solution to the supposed climate change that is being proposed. And that only solution is cap and trade, and that solution was proposed when they were talking about a new ice age back in the 70s, and also today when they're talking about the earth warming. When there's only one solution and it's enriching a very specific group of people who have invested millions of dollars in the cap and trade game, it's very obvious that there's issues with the science. We now look at another type of comparison. The number of predictions and type of predictions being made by the different models. Prediction questions. Qualitative prediction history. Remember, this is an example comparison, so we do not have the time to go into detailed analysis, as you can tell by some of the discussion earlier. But in this case, we're going to jump over a tremendous amount of data very briefly. We're going to provide some links here for those to follow who wish to look at the data in more detail. There have been 27 subquantum kinetic predictions that have been verified. There are dozens of places where predictions of relativity have not been borne out. Relativity was first to predict that gravity bends light, while an entrained aether also matches this phenomenon. It was not used to make the prediction. Being first to predict indicates either that a modeling tool might be easier to use to do predictions, or it just might be a historical fluke. But nonetheless, being first is a mark of benefit for a specific model. More prediction questions. Is it easy to make predictions with the model? String theory can't make predictions, and you can look at the book Not Even Wrong for more information about this. String theory is dead in the water because of this. Are quantification and simulation tools available? Relativity is more mature than subquantum kinetics with more precise quantification tools, and this is unquestionably a benefit for that model. Some might say that the Lorentzian relativity, which is in line with entrained aether, is just as quantification strong. Continuing with more comparison techniques. Computation. Comparing different models by their complexity. Complexity. The number of particles, submodels, elements, equations, dimensions, levels should be minimal or minimized. Do a significant number of features emerge automatically from other features? This reduces the basic number of elements. Unified field theory is actually a minus. It is better to not have fields as independent submodels at all. So the number of each field adds a level of complexity. If all fields emerge, as they do with subquantum kinetics, that is actually a benefit for that model where more things emerge. Within subquantum kinetics, there are 18 components, 7 subparticles, 5 interactions, 1 time and 3 space dimensions, as well as linear momentum. This is versus hundreds of components of the conventional model. For example, the number of quarks and other base particles, along with 10 plus dimensions for strings, linear momentum, angular momentum, dozens of atomic bonds and shells, quantum behavior, and many, many other features of the standard model, as it is a combination of many different intermodels. With subquantum kinetics, all of these elements or features or behaviors emerge from the simpler model. Subquantum kinetics emergence. The subquantum kinetic reaction diffusion space behaves different than a fluid dynamic space because the reactions provide an additional dimension of behavior. Spherical particles, light waves, electric field, magnetic field, and gravitational field structures all emerge. Gravity bending of light emerges due to the larger density of subparticles affecting the light wave structures. Normal emergence from linear momentum of energy, diffusion, angular momentum, and conservation is supported. There is no need for dark energy, dark matter, quarks, or the weak field. The perpetual atomic behavior emerges from an environmental flow of subparticles. And note how this correlates with video 3, where we saw that an essential element of energy, any form of energy, or continual energy, or perpetual energy, is some type of environmental flow. Quantum behavior emergence. Quantum mechanics is a probabilistic formulation without underlying dynamics. Electrons can disappear in one location around an atom and appear at another. With subquantum kinetics, electrons are vortexes of interacting subparticles balanced within a larger space of the atom where there are a multitude of other vortices. When one vortex in one location dissipates, another will form in another location to maintain the balance between all of the vortices. There's no need for magical quantum motion of a particle from one location to another. It's basically a vortex in one location. As it dissipates, another vortex will form in order to maintain the balance of all of the subparticle reactions within the space of the atom. With subquantum kinetics, wave-particle duality can be explained by how well electron vortices hold together. As electrons are accelerated, the vortex becomes more of a group of subparticles that interact as a wave within the larger subparticle field. The vortex reforms under conditions such as being hit by a light wave. Paradoxes and singularities. Another computation comparison technique for models, or between models. Paradoxes and singularities. Relativity has singularities such as the Big Bang and black holes. Popularly, these are held as exciting science fiction features. However, from a scientific and computational perspective, these are significant drawbacks. The best models, for example, subquantum kinetics, minimizes singularities. Circular elements, i.e. paradoxes, should be minimized. Relativity has the twin paradox. It's specifically the relative viewpoint. This is where it is difficult to determine which twin should age if both twins are accelerating away from each other. Subquantum kinetics does not have this paradox issue. We now finish off the computation comparison techniques with consistency, gaps, and openness. Consistency, gaps, and openness. As most modern scientific models have many submodels, the submodels should fit together smoothly, meaning there should be few gaps and each of the submodels should have similar features, creating consistency. As models are not reality but rather tools, openness is a significant benefit and is essential. It is not a drawback. You can see earlier videos for more information on this. As with computer systems, models need to be able to handle new features and data gracefully. There should not be a need to add new constructs or submodels as new data and observations become available. Consistency. Energy consistency. With linear momentum, energy is described as kinetic energy is equal to 1/2 of the mass times the velocity squared. In relativity, energy is described as energy is equal to mass times the speed of light squared. As kinetic energy and relativity energy are both energy, we simplify and get 1/2 of the velocity squared is equal to the speed of light squared, which is nonsense because the context or the submodels has changed between the two different equations. In order to create a consistent context between the two submodels, energy should be understood as, or can be understood as, the internal energy of moving subparticles that make up the vortex of each particle. So just as with the celestial and macro interpretation of energy, of being the combination of many smaller particles reacting with each other or their motion, you can also look at energy in a consistent way and say that the behavior of all of the subparticles and how they are moving and reacting with each other cause the energy for each particle. This creates a consistency of interpretation where energy is always the motion or macro motion of many smaller elements. Consistency in getting smaller. As we get smaller, as we make a transition from one model or one state to another, for example, from gross matter to molecules, from molecules to atoms, from atoms to particles, and then from particles to the next smaller level, is the transition of a similar nature? Do the different models have similar properties? With string theory, we have a gross consistency change where additional dimensions, an abstract nature, multiverses, time travel are all introduced. However, none of these are observable in the real world, and also it is a major consistency change in the behavior of the different integrated models. With quarks, we're continually seeing a growing number of particles. Most are highly stable. There is also a small change of size from particle to quark, a basic 3-to-1 ratio, never any greater. The predictions are also almost entirely within a particle, a rarefied particle space where you have accelerators. And all of the resultant particles are also unstable. In addition, there's a vast body of anomalous behaviors within physics that are not being handled by these models. Subquantum kinetics, however, provides a form for working with anomalous behavior, where the term form is basically there is an easy way to construct the anomalous behavior using the type of reaction diffusion or fluid dynamics computation space to represent much of the anomalous behavior. In addition, there's a large number of subparticles that make up particles, just as there's a large number of molecules that make up the micro-macro space. The reaction diffusion behavior is non-discrete gradations, which is similar to other observable phenomena in the real world. Openness. We will be looking at a large set of examples here, so this section will be broken up into different parts. Basics of openness. The goal is to have a computational model to map data. None will be perfect. Many may match or have benefits in different ways. Openness is advantageous where the model can be tweaked to capture additional behavior without adding additional constructs. There are many different and very varied types of openness. The space of the models, intermediary behavior, the emergence of alternative models, and the breadth of phenomenon. Each of these will be visited in turn. The space of models. The space of subquantum kinetic models. The current subquantum kinetic model has a specific set of equations and variables. The variables and other elements of the equations are being investigated to see which best set matches the data of the real world. Additional elements could also be added or removed from the equations. The number of different types of subparticles, how the subparticles react with each other, and also diffusion rates are other ways of modifying the model. This enables a very large space of different subquantum kinetic models. Other computational models for reaction diffusion or computational fluid dynamics could be used. For example, cellular automaton. So variation in the space can be by the elements, but also by the modality of computation. None of this adds constructs. All of the above only fine-tunes the specifics of a general reaction diffusion model or subquantum kinetics model. The space of relativity models. Relativity integrates the meta level of the external space to the ordinary level items within the space. This locks the ether and space very rigidly, not allowing freedom of behavior. In computer science, there's a concept of obfuscation of code, where code is written in a very compact and efficient manner. However, it is so dense that much meaning is lost, and this is considered today as being not advantageous, as being actually a roadblock. In a number of ways, this is what is done with the relativity representation of ether/space. For there was a great favoring of relativity because it simplified the equations or the representations. You didn't have to talk about additional elements such as ether. So in some ways, this is an equivalency mapping of obfuscation. Intermediary behavior. Subquantum kinetics. Behavior beyond the discrete. Subquantum kinetics allows complex micro-macro domain behavior emergence. For example, magnetic, electrical, gravitational behavior for subparticles in the more general space can emerge. This is behavior beyond just behavior at particle gradations. So while there might be behavior built into how particles interact, a lot of the field behavior can be emerging from the subparticles and how they are interacting within currents or wave patterns or other types of standing structures beyond just the particle level, where we see some form of gravitation and electromagnetic formation and spin formation within particles. There can be spin variation. You don't have to have discrete levels of spin. You can have gradations of spin instead. There can be parthenogenesis, where there's creation of new particles. There can be non-stable formations, such as the particles that are created within highly accelerated environments of some of the more expensive science experiments occurring today. There's no need for quarks with this type of model. There can be other types of particles or molecules within HHO experiments and Ormus experiments. There's been observation of very unusual behavior of particles where we're seeing monatomic molecules for materials that usually are combined with numerous different molecules. There can be an existence of additional environmental energy. So we have a standard model of energy at the macro level and the celestial level, but when we move into the atomic, particle, and subparticle level, we have a completely different definition of energy, because momentum definitions have changed, because we're working with quantum and wave models. So the question is, we understand where environmental energy comes from the celestial and from the macro perspective, but is there additionally some type of environmental energy? And subquantum kinetics talks about how that environmental energy can operate at the subparticle level. There can also be overlapping behaviors with sound, light, and other waves. And there have been experiments where people have seen combinations of sound, light, electromagnetic, gravitational, and other forces combining together to have effects. Vacuum properties can also have physical foundation within the subquantum kinetics model. So this type of model allows intermediary behavior. So the big issue here that we're trying to get across is you need to have an effective model where you can have intermediary behavior. Everything is not stuck at discrete points. Historically, those discrete points were useful because the computation was too hard to do. But with computers now, we can do far greater amounts of computation, so that allows us to now start looking at models that have gradations of behavior and other forms of behavior. And at this level the level of maturity we now have in science and the tools that we're working with, we want to take advantage of the computational tools and start looking at the intermediary behaviors and fostering models to have intermediary behaviors. Emergence of alternative models. Emergence of alternative models. For a model to be good, it should be able to subsume other models that have proven success in matching some data. Many alternative models of basic physics have been proposed throughout the decades, many of which match significant bodies of data. Most of these models can emerge from subquantum kinetics. For example, Shipov describes non-discrete behavior around the spin of particles using relativistic equations. This additional behavior can be captured within subquantum kinetics via subparticle behavior both within and outside of particles. Russell, Mile, and others describe electric behavior that is more complex and covers cosmic spaces and vortices. Subquantum kinetics allows electric behavior outside the confines of particles via subparticle behavior. Leeds-Skalnin has identified magnetic behavior that is not explained by the conventional model, but fits better with a magnetic model flow in two different directions. This can be captured by the two subparticles in subquantum kinetics responsible for electricity. Different flow rates for these subparticles could lead to different structure formations and gradations, mimicking magnetic flow, electric flow, light waves, and radio waves. Finally, we talk about models taking in a larger breadth of phenomenon. Quantum entanglement. With subquantum kinetics, diffusion and wave structure creation rates can differ between subparticles. Experiments have shown many orders of magnitude faster than speed of light reactions. For example, Korziev in the 1950s and others noted that the sun affects bacteria growth at 10 orders of magnitude faster than the speed of light. Von Flandern predicts that gravity operates, again, at about 10 orders of magnitude faster than the speed of light. Coherent information from Sirius is being received almost instantaneously in some very recent experiments. Quantum entanglement tunneling is consistent with varying subparticle diffusion and also structure creation rates within the subquantum kinetics model. HHO, or water broken into its constituents. The author has witnessed HHO welding torches, where the fire is very directed and also cool. You can pass your hand through the flame with only a very mild warm feeling. You can hold your finger millimeters from the flame and there is no heat whatsoever. The metal around the emerging gas, burning gas, is also not heated at all. The flame is highly directed and will burn right through metals very quickly. HHO can be created via electricity, sound, vibration, and a number of alternative methods. This phenomena is not explained by the standard model, yet there are production tools on the market. Research suggests that a gas heavier than oxygen or hydrogen is being created and is what is creating the unusual behavior. As particles are vortices of subparticles, they can be potentially disassociated via different means, and their internal subparticle motion energy can be made accessible. This could potentially be a way of precisely modeling HHO behavior. Water crystalline structures. There is a fourth phase of water, which is a two-dimensional lattice of H3O2 that forms next to different materials. 100,000 layers of the replicated lattice can be created, with the lattice degrading as it gets further from the material. This could be the mechanism for homeopathy, as well as other experiments with water memory. Where water remembers materials it contained long after the material has been diluted out. Other crystal structures can potentially form within water and other structures. It has been proposed that a crystalline funnel of hydrogen and oxygen might be what creates the HHO heavy gas. Other crystalline structures. Cold fusion. This is where there's a metal matrix that has simple atoms, e.g. hydrogen or deuterium, pushed inside via electromagnetic stimulation. Further electromagnetic stimulation of the matrix creates parthenogenesis, so that new electrons are created so that the deuterium forms helium and other materials. This easily fits within the subquantum kinetics model, as new particles can form, particularly in the neighborhood of other particles and external subparticle motion. Vortex behavior. Particle vortex behavior can be modeled with subquantum kinetics. The spin of particles can be at upper or lower edges of the gradations, the fixed gradations that particles spin at. Changes in spin can make the particle or a particle structure, such as an atom, molecule, or crystalline matrix, go beyond the gradations and change. External subparticle flow can be affected or can affect any of these structures. Observed macro-micro behavior of this type of phenomenon. Tornadoes and hurricanes have been known to meld matter together. Some experiments have either disassociated matter or melded it together. Swirled water has affected how water behaves. For example, plants grown with such water grow much faster. Spin transformation. Subquantum kinetics provides a modeling space where mechanisms for transformation of angular momentum into both gravitation change and linear momentum can be created. Observed behavior. A gyroscope spun on a pendulum on wheels will move forward after a full back and forth swing. The local weight of a spinning object will change so that the object can be easily lifted. Material subparticle flow. Bedini found that the energy in a capacitor bounces back to about 10% after a charge is dissipated. It's as if the materials themselves create a particle-subparticle flow. Qi experiments, which is part of Chinese medicine for thousands of years, has found that significant amounts of research showing biological effects, including effects over thousands of miles. The author's Qi experiments have identified a potential correlation between Qi flow and combinations of dielectric contact with conductors, crystals, light, sound, and magnetism. It's analogous to different materials touching each other, creating an electric flow. Here, different materials or a matrix can create a subparticle flow. Large body of phenomenon. Any physics model needs to account for all observed phenomena and also all to be observed phenomenon. Phenomenon cannot be excluded simply because it does not fit the existing standard model. There should never be but one standard model. There should always be a multitude of them, and there should always be a comparison of them based on characteristics. Subquantum kinetics provides a medium for a large body of observed phenomenon, beyond what has just been talked about, and I'll just list off a very few. Morphic or psychic fields, alternative health fields, pyramid power, water bridges created by electric stimulation of water, expanding earth or parthenogenesis. This is analogous to the model of Pangea being round, just like science eventually came around to the world being round. Gaps. Every model has them. Gaps in subquantum kinetics. The specific equation parameters have not been fully worked out. At this point, you can only match one particle. Why are subparticles reacting with each other to form other subparticles? What makes them stick together? What is their geometry? Much of this would be worked out at the next level of research. First, the basics of subquantum kinetics, which basically captures a huge body of behaviors. Then you would go to the next level. It's like moving from molecule to atom, then atom to particle, then particle to subquantum kinetics, then subquantum kinetics to internal subparticle behavior. Why would some subparticles diffuse faster? Again, the question would be, what is their geometry to make that happen? Other major open questions include, how is all the anomalous behavior that we've talked about before be precisely modeled or captured within subquantum kinetics? Most of the precise modeling is still open in regards to what we have talked about in this presentation. We finally come to our last comparison technique, the mind, or rather, the mind mapping to the model, or the model being understood by the mind. Any model that you have needs to be easily understood by the mind and worked with by the mind. And this can include tools to make this happen more effectively. Through tools or basic reasoning, understandability, which is also a method within software engineering, is the model accessible to more than just a few cognoscenti? Part of the motivation for relativity was that you didn't need extra ether terms. However, it is a case of obfuscation where equations hide elements that provide not just openness and consistency, but also understandability. Usability. Are there graphical user interfaces or other tools available for the average investigator to work with easily? For example, direct simulation of interaction as opposed to going to functions, then to computation and simulation. There are different types of tools that do simulation, and they behave differently, and how people understand how they're working and how they can observe how they behave differs from a complexity level, from a usability level. So the question is, which type of simulation tool is more usable, easier to work with? Other examples of the current subquantum kinetics simulation goes to a functional representation, then to a computational representation of interaction. Is that more usable than, let's say, a cellular automaton representation, which would be a direct simulation? You would have to have both tools in front of you to work with. This is a major element of models. Model is not just the theoretical, but also the practical utilization. Can you create effective user tools for the model? There are also numerous different types of reaction diffusion computational systems that are being investigated by many different types of researchers. And all of these different types of reaction diffusion systems could be used within subquantum kinetics research.